Hello everyone, I'm Gongjin. Welcome to 2026 ESAT Chemistry class. This brand new course was developed by UEIE in 2026. Hello everyone, this is the ESAT demo lesson. Today we'll cover the key content from section C5 and C12 of the ESAT syllabus, redox reactions and electrolysis. Redox reactions are far more than just exam material. They link many areas of chemistry and help us understand the properties of substances and how chemical reactions take place. Next, we'll explore the application of redox reactions in electrolysis. Let's map out what we're covering. The core content here follows ESAT's official requirements for redox reactions. We need to master 6 key points. You can see the syllabus progresses step by step, from basic definitions to core concepts, and finally, practical skills. This is ESAT's official requirements for electrolysis. It covers key terms, redox rules, product prediction, half equations, and electroplating. By the end of class, you should achieve these 4 learning objectives. It's not just about identifying reaction types or doing calculations. We'll learn how oxidation states function and how to quickly recognize oxidizing agent. These are the learning objectives for electrolysis. First, we'll go through the fundamental knowledge. The last part is extended content, metal refining, another key application of electrolysis. This is extra material beyond the core syllabus. Alright, let's begin. Let's briefly go over the timeline for the lesson. We'll use examples to explain core concepts step by step. The short quiz helps you to review and consolidate what you've just learned. Practice A covers basic knowledge and skill application. Practice B includes more difficult exam-style questions to improve your problem-solving skills. The whole lesson takes about 2 hours, and you can learn at your own speed. Let's start with the basics, defining redox reactions in terms of oxygen. Here's an easy rule to remember. Gaining oxygen means oxidation, while losing oxygen means reduction. Take the first example. When carbon burns in oxygen to form carbon dioxide, carbon gains oxygen, so carbon undergoes oxidation. Now, the second example. Copper oxide reacts with hydrogen to produce copper and water. Copper oxide loses oxygen, so copper is reduced. One key rule you must keep in mind. Oxidation and reduction always occur simultaneously. They cannot happen separately. If one substance gains oxygen, another must lose it. There are no exceptions. Let's test what we've learned with a quick example. The question asks, which equation shows an oxidation reaction? Remember the rule. Oxidation means gaining oxygen. Take option A. Carbon reacts with oxygen to form carbon dioxide. Carbon clearly gains oxygen, so this is an oxidation reaction. The other options involve no gain or loss of oxygen, so they are not oxidation reactions. Now, let's move on to the essence of redox reactions, electron transfer. This is the fundamental explanation. Let's set aside the oxygen rule for now. Here's the new definition. Losing electrons is oxidation, and gaining electrons is reduction. When an atom loses electrons, its oxidation state increases. When it gains electrons, the oxidation state decreases. Take the reaction between zinc and copper sulfate as an example. Zinc atoms lose 2 electrons and turn into zinc ions, with their oxidation state rising from 0 to +2. This is oxidation. Copper ions gain those 2 electrons and become copper atoms, with their oxidation state dropping from +2 to 0. This is reduction. Keep this in mind. Electron transfer is the root cause, while changes in oxidation states are just observable phenomena. Grasp this. Redox reactions will become much simpler. Let's apply the concept of electron transfer to this problem. We're looking at the reaction between iron 2 chloride and chlorine gas, which produces iron 3 chloride. Let's check the oxidation states. Iron changes from +2 to +3. It loses 1 electron, so it undergoes oxidation. Chlorine gas goes from 0 to -1. It gains electrons, so it is reduced. As you can see, identifying oxidation and reduction becomes really straightforward once you focus on electrons and oxidation states. To work with redox reactions, we need a useful tool, oxidation states. You can think of an oxidation state as the hypothetical charge an atom would carry if the compound split apart completely. It acts like a label showing how many electrons the atom has gained or lost. Let's go through 6 essential rules you will use all the time. 1. Pure elements have an oxidation state of 0. 2. Some elements have fixed oxidation states. For instance, group 1 elements are always +1, and oxygen is generally -2. 3. The more electronegative element takes on a negative oxidation state. Take sodium hydride as an example. Hydrogen is more electronegative than sodium, so its oxidation state is -1. 4. The sum of oxidation states in a neutral compound equals 0. 5. For simple ions, an element's oxidation state is the same as the ion's charge. 6. In a polyatomic ion, the total of all oxidation states equals the overall charge of the ion. Be sure to memorize these rules. They will simplify your calculations a lot. Let's practice calculating oxidation states and put these rules into use. First up, sulfuric acid. Hydrogen is +1 and oxygen is -2. We set up the equation and solve it. So we get sulfur is +6. Simple enough. Next, the permanganate ion. Oxygen is -2, and the overall charge of the ion is -1. So we set up the equation, and the calculations show manganese is +7. Now let's work on this practice problem. Find the oxidation state of chromium in sodium dichromate. Sodium has an oxidation state of +1, and oxygen is -2. Set up the equation. Solve it, and we get chromium is +6. So the answer is option C. Follow these steps, and you will always get it right. Now that we know how to calculate oxidation states, let's classify reaction types. The rule is straightforward. If oxidation states change, it's a redox reaction. If not, it isn't. Let's test this. Take zinc reacting with hydrochloric acid. Zinc's oxidation state rises while hydrogen's falls. Clear changes. So this is a redox reaction. For the reaction between hydrochloric acid and sodium hydroxide, all oxidation states remain unchanged. So it's not a redox reaction. That's the gold standard. Forget everything else, just check for changes in oxidation states. Let's see if you can spot the oxidation-only equation here. Remember, oxidation is losing electrons. Let's look at equation B. Hydroxide ions are losing electrons to form oxygen gas. There's no species in this equation that's gaining those electrons, so it's only oxidation happening. The other equations either have both oxidation and reduction, like A, only reduction, like C, or nothing, like D. So the answer is B. Great job if you got that right. Now let's talk about a cool special type of redox, disproportionation. Here's a rhyme to remember. One substance, one element, both up and down. Let's break that down. Same substance, same element, but part of it gets oxidized, oxidation state up, and the part gets reduced, oxidation state down. Take chlorine and water. Chlorine reacts with water to make hydrochloric acid and hypochlorous acid. Chlorine in chlorine molecule is 0. In hydrogen chloride, it's -1, reduced. In hypochlorous acid, it's +1, oxidized. Same element, chlorine, same substance, chlorine molecule, both up and down, disproportionation. It's just a fancy word for one element doing both oxidation and reduction in the same reaction. Let's confirm if this reaction is disproportionation. The reaction is chlorine with hot sodium hydroxide. Let's check the oxidation states of chlorine. In chlorine molecule, it's 0. In sodium chloride, it's -1, so that's reduction. In sodium chlorate, it's +5, so that's oxidation. The same element, chlorine, in the same starting substance, chlorine molecule, is both oxidized and reduced. That's the definition of disproportionation. So yes, this reaction fits perfectly. Last but not least, identifying oxidizing and reducing agents. Here's the rhyme that will save you on exams. Oxidizing agent gains electrons. Oxidation state decreases. Reducing agent loses electrons. Oxidation state increases. Let's use our old friend copper oxide reacting with hydrogen. Copper goes from +2 to 0. Gains electrons, oxidation state down. That's the oxidizing agent. Hydrogen goes from 0 to +1, loses electrons, oxidation state up. That's the reducing agent. And remember electron conservation. The electrons in oxidizing agent gains equal the electrons the reducing agent loses. It's a perfect balance. Let's put this into practice with a simple reaction, magnesium and acid. Let's find the oxidizing and reducing agents. Magnesium goes from 0 to +2. It's losing electrons, so it's the reducing agent. Hydrogen ions go from +1 to 0. They are gaining electrons, so they're the oxidizing agent. Okay, now we can explore the application of redox reactions in electrolysis. First, let's put the concept more clearly. Electrolysis is the process of using electricity to break down an ionic compound, but it only works if the compound is molten or dissolved in water, so the ions can move freely. The substance being broken down is called the electrolyte. We use two electrodes to connect the electrolyte to the power supply. The anode is the positive electrode, and the cathode is the negative one. Notice, we use inert materials like carbon for electrodes, so they don't react with the electrolyte. We want the electrolyte to change, not the electrodes. Let's work through the example question in past paper. Which statement about electrolysis of lead-2 bromide is correct? Statement 1. Lead is formed at the negative electrode. In electrolysis, positive ions are attracted to the negative electrode. For molten lead-2 bromide, lead ion is positive, which is attracted by the negative electrode and is reduced. Thus, lead is formed at the negative electrode is correct. Statement 2. Anions are attracted by positive electrode, releasing electrons to the positive electrode. Electrons flow through the external circuit to the negative electrode, where they are accepted by cations. So statement 2 is correct. Statement 3. Write the half equations. At cathode, one lead-2 ion gains 2 electrons to produce one lead atom. At anode, 2 electrons are released by 2 bromide ions, producing 1 bromine molecule. So the molar ratio of bromine molecules and lead is 1:1, not 2:1. Statement 3 is incorrect. Now, why do we use a direct current power supply and not alternating current? Think about it. In electrolysis, we need specific things to happen at specific electrodes: reduction at the cathode and oxidation at the anode. If we use alternating current, the positive and negative terminals would flip back and forth really fast. The electrodes would keep switching roles, and the reactions would just undo themselves immediately. No net chemical change would happen. Direct current gives us a fixed positive anode and a fixed negative cathode, so the reactions can proceed in one direction and produce a result. Now, for the core of electrolysis, what happens at the electrodes? Let's start with the cathode, the negative electrode. Positive ions, called cations, are attracted to it. When they reach the cathode, they gain electrons. This is reduction. For example, copper ions gain electrons to become copper metal. Now the anode, the positive electrode. Negative ions, called cations, are attracted to it. When they reach the anode, they lose electrons. This is oxidation. For example, chloride ions lose electrons to become chlorine gas. This process of ions losing their charge at the electrodes is called discharge. Remember, cathode is reduction, anode is oxidation. Let's apply this to a simple case: electrolyzing a molten binary compound, like lead-2 bromide. First, we melt the solid lead-2 bromide, so the ions are free to move. At the cathode, the positive lead ions gain electrons and turn into molten lead metal. You will see a shiny liquid forming. At the anode, the negative bromide ions lose electrons and turn into brown bromine gas. You will see bubbles and a brown color. This is straightforward because there are only two types of ions present. Let's test your understanding with a quick question. What do we get when we electrolyze molten sodium chloride? Think about the ions present, sodium ions and chlorine ions. At the cathode, sodium ions gain electrons to become sodium metal. At the anode, chloride ions lose electrons to become chlorine gas. So the answer is A, sodium metals and chlorine gas. That's how we produce sodium industrially. Things get a bit more complex when we electrolyze aqueous solutions because water itself is a very weak electrolyte and splits into hydrogen ions and hydroxide ions. So in addition to the ions from the salt, we have these water ions to consider. Let's take concentrated sodium chloride solution as an example. We have sodium ions, chloride ions, hydrogen ions, and hydroxide ions. At the cathode, hydrogen ions are discharged instead of sodium ions because hydrogen is much less reactive than the sodium, so we get hydrogen gas. At the anode, even though hydroxide ions is slightly easier to discharge, there are so many more chloride ions that they get discharged instead, so we get chlorine gas. The remaining sodium ions and hydroxide ions form sodium hydroxide. This is the industrial process for making sodium hydroxide. To predict what happens in aqueous electrolysis, we need some simple rules. At the cathode, it's all about the reactivity series. If the metal in the salt is more reactive than hydrogen, like sodium and magnesium, hydrogen gas is produced. If it's less reactive, like copper, silver, the metal itself is produced. At the anode, it depends on the ions. If we have halide ions, like chloride, bromide, iodide, we get the halogen gas. For almost any other ions, like sulfate or nitrate, we get oxygen gas from the water's hydroxide ions. These rules will help you predict the products for almost any aqueous solution. Let's use our rules to solve this problem, electrolyzing aqueous copper-2 sulfate with carbon electrodes. What ions do we have? Copper ions, sulfate ions, hydrogen ions, and hydroxide ions. At the cathode, copper is below hydrogen in the reactivity series, so copper metal is produced. At the anode, sulfate is not a halide, so we get oxygen gas from the hydroxide ions. So the products are copper metal and oxygen gas. Answer A. The blue solution will fade as the copper ions are removed, and the solution becomes sulfuric acid. Now, let's learn how to write half equations. These show exactly what's happening at each electrode, including the electrons. Here's a step-by-step method. First, identify what's reacting and what's being produced. Then, balance the items, starting with everything except hydrogen and oxygen. Next, balance oxygen by adding water. and hydrogen by adding hydrogen ions. Finally, balance the overall charge by adding electrons. Remember, electrons on the right mean oxidation, losing electrons, and electrons on the left mean reduction, gaining electrons. Let's practice with the electrolysis of water. Can you see how the electrons balance out? Let's write the half equations for electrolyzing molten magnesium chloride. At the cathode, magnesium ions gain 2 electrons to become magnesium metal. The half equation is 1 magnesium ion plus 2 electrons, producing 1 magnesium atom. That's reduction. At the anode, chloride ions lose electrons to form chlorine gas. We need 2 chloride ions to make 1 chlorine molecule. So the equation is 2 chloride ions, producing 1 chlorine molecule and 2 electrons. That's oxidation. Notice how the electrons lost at the anode equal the electrons gained at the cathode. Charge is conserved. Now, let's look at a real-world application of electrolysis, electroplating, coating one metal with another. Why do we do this? To make things look better, like silver-plated cutlery. To prevent corrosion, like chrome plating on a car. Or to make a surface harder. Let's take silver plating a spoon as an example. The anode is a piece of silver metal, which dissolves into silver ions. The cathode is the steel spoon we want to plate. The electrolyte is the silver nitrate solution. Silver ions from the anode are attracted to the cathode, the spoon, gain electrons, and deposit as a thin, shiny layer of silver. The result? A beautifully silver-plated spoon. Let's test your understanding of electroplating. If we want to coat an iron nail with zinc, what do we use for the anode and electrolyte? Let's think. The anode should be the metal we want to plate, zinc. It dissolves to provide zinc ions. The electrolyte needs to contain zinc ions, so zinc sulfate solution is perfect. The iron nail is the cathode, where the zinc ions are deposited. So the correct answer is C. Anode is zinc metal, electrolyte is zinc sulfate solution. Another important application is refining copper. Copper ore gives us impure copper, which isn't good enough for electrical wires. Electrolysis to the rescue. We use an impure copper anode and a pure copper cathode, with copper sulfate solution as the electrolyte. At the anode, the impure copper dissolves into copper ions, and the impurities fall to the bottom as sludge, which can contain precious metals like gold. At the cathode, the copper ions gain electrons and are deposited as pure copper metal. This process gives us copper that's over 99.9% pure, perfect for conducting electricity. Let's work through this copper electrorefining example step by step. First, let's recall the setup. We have the impure copper anode, a pure copper cathode, and aqueous copper 2 sulfate as the electrolyte. This is the standard setup for purifying copper, and we need to identify the correct statement. Let's go through each option. Option A. The cathode is where reduction happens, and only copper ions are reduced to pure copper here. Impurities do not deposit on the cathode, so A is wrong. Option B. The anode is impure copper, not pure. The copper in the impure anode dissolves, but the statement say pure copper dissolves from the anode, which is misleading and incorrect. Option C. This is exactly what happens at the cathode. Copper ion gains 2 electrons and is reduced to pure copper metal, which deposits on the pure copper cathode. This is the correct answer. Option D. Gold and silver are less reactive than copper, so they do not oxidize or dissolve. Instead, they fall to the bottom of the cell as the anode sludge, so D is wrong. Option E. For every copper atom that dissolves from the anode, 1 copper ion is reduced and deposits at the cathode. The number of copper ions in the electrolyte stays the same, so copper sulfate concentration remains constant. E is wrong. Here comes the quiz. There are 18 questions in total, and you need to finish it within 25 minutes. It's recommended that you take it right after watching this video for the best results. These are 2 sets of exercises with suggested time limits. Practice A covers basic knowledge and skill application. Practice B includes more difficult exam-style questions to improve your problem-solving skills. It's recommended that you complete the 2 sets of exercises at separate intervals to help you review what you've learned. Thank you for watching the video. Bye!